Welcome to a lesson with Dr. Powell. Let's take a look at Shroeder Bernstein's theorem. It states that given an injection one way, an injection the other way between two sets, that we actually have a bijection. Now, an equivalent form of saying this is as follows. If we think about B injecting into A in the following way. So think of A as being some set and B injects into it. So it almost as if it can live inside of it, which makes sense since B is an injection where its image lies inside of A. But a function is always a surjection onto its image. So in other words, B is in bijection with a subset of A. So we can kind of think of that subset as being labeled as B itself. So you can think of B as being a subset of A. But likewise, if we go the other way, we can think about A as being a subset of B itself, meaning that all of A is in bijection with the subset of B. So if we do a little relabeling here and think of nesting, we can think about three sets. A is inside of B is inside of C, where A and C are actually in bijection correspondence with each other, because C was labeled as A before. And so the theorem states that if we have a nesting like this, and A and C are in bijection with each other, then A and B have a bijection between each other. And so that's kind of the way we can think about this. Now, let's suppose that we have a function that goes from A to C that's a bijection. So that's kind of the assumption here is we have a function that goes from A. So we're going to work through the proof of this theorem. So let's suppose we have a bijection F, and what we'd like to show is that we actually have a bijection from A to B. Okay, so if we have a bijection from A to C, then we will have a bijection from A to B. Now, of course, if A, B, and C are all finite sets, this is rather simple because, I mean, the sandwich B would be the same, basically. However, in the infinite case, this is more interesting because B doesn't necessarily have to be the same as A or C, and these inclusions can be strict inclusions. Okay, so we start with this bijection, and this is a bijection, and we want to build, based off of this, a bijection that goes from A to B. So we're going to do this by fiber bumping. Now, what is a fiber? It's the preimage of a singleton set. So we start with this function f, and we're taking things in A and sending them to all of C in bijection correspondence. Now, there's some problems. So A, the things in here can be sent out to C out here, and we'd like to kind of rearrange things so that it's just sent to here in B, but such that every fiber only has one guy in it. Because another way of saying injective is to say that every fiber or every preimage of a singleton point has just one thing in it. So each fiber should have size 1. So fibers need to have just one guy in it. Fibers just have one thing. And then, of course, we want all of B to be hit. So we want that to maintain there. And if B is hit and every fiber has one thing, and we've modified F in such a way, then we'd be done. Then we'd have a function G, a bijection G that goes from A to B. And that would actually prove this theorem, this Shroeder Bernstein theorem. Okay, so, well, let's start modifying it. The first thing that we see is everything that's in A that's wanting to map out here to C, let's change its destination. Let's change its destination so it maps to itself. Okay, so that's the first modification. That's like stage one modification. So let's suppose we have an element of A, and this element of A used to map to C. So now we're going to let it map to itself. This means that, and we're modifying the definition of F. So let's just think about what we're doing. So what we're doing is we're taking everything that maps to A, and it already had something in it because this was a bijection to all of C in particular. So particular A was already hit here, and so perhaps it already had something in it, and something else in another fiber was going out here, and fibers are distinct from each other for a function to be well defined. So so what we have is this fiber. Now we're throwing an A into it, even though it had something else going to it before. Maybe it had like Y. Okay, so it had something like Y that was hitting A, but now we're throwing A in there to hit A as well. So if we make this first modification, what we've done is we've created a function that's not an injection anymore, but it is a surjection onto B, because everything in B is still hit. The only fibers that we modified with things that were out here, right, that we did away with. So we did away with the fibers that went out here. We made those guys empty and replaced the domain elements from A into new fibers, so that we were hitting things here. So we're kind of double hitting things now, but everything in this B section is hit. And we're going to maintain that now throughout. So we're not going to be changing the codomain. So it's going to be surjective the whole time. Since we're not going to throw everything out of any more fibers, we're just going to be bumping things from fibers to another. So the only problem now is that we've produced a lot of fibers that have two things in them. So now we have to bump those things out into other fibers. And so these will only have one thing in them. So what are we going to bump? Well, this is what we're going to do. So here in these fibers, we're going to take the guy that originally in the original function was actually heading to A, but now we've put a new thing that was heading to A. We're going to take that guy and we're going to bump it out of this fiber. We're going to put it into a new fiber. We're going to put it into the fiber over Y itself, meaning we're going to send Y to itself now. Now, the fiber where the way we engineered these fibers, right? So we have Y is so one of these guys in the fiber was actually heading toward this element, and was heading toward this guy, right? Now Y itself was heading toward A, so Y could not have been in this fiber, which means this fiber was still just one thing. So it was distinct here. And so this fiber was very different than any of the fibers we had in the stage one. So it still had only one thing in it. So from this stage, we bump these out into things in stage two. And these guys will now have a fiber, fibers of size 2, and these ones from stage 1 now will only have fibers of size 1. And all the while, we have not changed the codomain of the function, so it's still surjective. We just kind of bump stage 1 fibers now to make them have one thing in them, and stage 2 fibers will now have two things in them. Okay, now what do? We go to stage 3. And we do a similar idea. So here things have two, so we can kind of think about the same argument here, just just by symmetry, kind of replacing things, where we're looking at this fiber here now has two things, and we'll keep Y in it, but we'll bump the other thing out of it. Now that thing will go to the fiber, a fiber that has not been considered yet, not even in the original in the original thing. So once we've hit a fiber, this has one thing in it, and it already has it going to itself. So we can kind of throw it out because we're not going to deal with A's, like we're not going to deal with this A again. Just like here, we're not going to deal with the Y again in another fiber in another stage. We're always kind of going to another thing. So the fibers we have from one stage to another are very distinct from each other. So we can kind of partition the element or the different stages that way. They're going to be very distinct fibers that are going to be affected. So in this process, we have two things happening. Either a fiber of this map, as we modify it, will be, so fibers are uniquely determined by elements of B here now. So for every element of B, so take any element of B, either the fiber over it will be eventually affected by this process in one of the stages, or it'll never be affected by one of these stages. Now, if it is affected by one of these stages, then after it's been affected, it'll have just one thing in it. Now, if it's never affected by these stages, then it'll never have two things in it. It'll just have one thing in it. So the idea is, by induction, even after all of these after all the fibers are affected, and eventually through the process, you can even define this new function as being at a particular point, A, to another one by thinking about having a fiber being affected or not. And if it is affected, it'll eventually be gotten to. You can actually define it that way. So either fibers will be affected or won't be affected. And in either case, after this process is done, or through the process of, or through the sequence of this process as the definition for this function, we actually get fibers only have one thing, and it is surjective, which actually creates a bijection from A to B. Thanks for watching.